Okay, so we're in the home stretch. Let's finish this up. Um, so let's talk about formal charge for 61. Formal charge is going to be the group number minus number of bonds plus number of free electrons. So anything, any dots that are left. And each atom is going to get its own essentially formal charge. When we're dealing with formal charge, we always want to reduce to zero ideally. We don't want positive next to positive or negative next to negative, and we want to minimize as much as possible. So if this is our structure right here, sulfur, each of these is going to have its own formal charge. So what is the formal charge of sulfur? What is the formal charge of carbon? What is the formal charge of nitrogen? Give myself a little more room. What is the formal charge of carbon? What is the formal charge of nitrogen? So all of these, here we go. And we'll put it on the atom after, but just so we can show the calculation down here. Formal charge of nitrogen. Okay. So group number. Sulfur is in group 6 minus the number of bonds. It has 2 bonds to it plus the 4 electrons that are attached. So 6 minus 6 gives sulfur a formal charge of 0. Carbon, it's in group 4 minus, it has 4 bonds to it and no free electrons or no dots on it, a 0 formal charge. Nitrogen, group 5 minus the 2 bonds plus the 4 electrons. 5 minus 6 gives me a -1. So you note if you add up all the formal charges, you should get the charge of the actual structure itself. And so there we go. So which of the following is correct? 0 for 0. There we go. D. We should get D for this one. And off we go. It's pretty good. We want nitrogen to carry the formal charge because it is more electronegative than sulfur. And all right, Lewis structure of XeF2. So we're going to follow the same exact rules for XeF2. Xenon is in group 8. Fluorine is in group 7. So xenon is in group 8. Fluorine, there are 2 of them in group 7. So 14 plus 8 gives us what? 22, right? 14, yep, 22. So there we go. There's our count of electrons. Next, I'm going to put xenon in the middle. Because it's first, we also generally put it in the middle, and it's in the middle here for all of these. I've just used 4 electrons. So I have 18 electrons left. I used 4 because 2 bonds. I have 18 electrons left. I'm going to take care of the peripheral atoms. So the fluorines get 6 electrons each. So that would be 12. That gives me 6 electrons left. Next, xenon is going to get the rest. I'm going to add the remaining 6 to xenon. And there we go. It is good to go. We don't generally form multiple bonds with halogens, especially fluorine. So we absolutely could eliminate those right off the bat. And it comes down to how many are on the central atom. So B for this one, 62. Next up, what is the delta H for the reaction of the combustion of H2 rate based on bond enthalpies? So we actually have to draw these bonds out. And we're going to talk about this in 2 ways. Well, in 1 way, really, but breaking bonds costs energy. We have to put energy in. So we're going to always designate those as a positive. Like we're going to essentially, that costs us energy. Forming bonds is going to release energy. So that is going to be negative. So if we look at this compound, if we look at this formula right here, hydrogen bound to hydrogen, I also have 1/2 of an oxygen bond, which is double bond O, and I have, so that is what we're doing, okay? So if we take a look at the energies involved here for the breaking of the bonds, which is going to be this side, right? Breaking. We're going to break a hydrogen-hydrogen bond, which is 436. So this bond right here, just one of them, is 436 kilojoules of energy. Plus, we're going to add to that. Let me see, how am I going to do this? There's not a ton of space here. So let me do it this way. Hydrogen, hydrogen is equal to 436. And we're just breaking one of those. Next, we're also going to be breaking, because the half is out front, that oxygen-oxygen double bond, which is 1/2 of 498. And let's add those two together. So we'll just basically say 1/2 of 498 divided by 2. So 249 plus the 436. So in order to break those bonds, it will cost me 685 kilojoules of energy. So that's the cost to break the bonds. And to that, we also are going to deal with the other half of this, which is H2O. I have 2 OH bonds, right? Which is equal to 2 times the OH, which is 464. Okay. So 464 times 2, 928. So overall, that is 928. But because that's forming, because we're creating these, this is a negative 928. So we take that negative 928, and we essentially add it to the total. So negative, it's gonna cost us 685 to form the reactants, minus the 928, because we're gonna get essentially, because we're essentially forming 928 kilojoules worth of bonds. So 685 minus 928 gives us negative 243. So this one should be C. Okay, so all of the bonds you form cost energy, so they're positive. All the forming bonds are negative, sorry, and breaking bonds is positive. We break all the reactant bonds, we form all the product bonds, and then we just total it up, essentially. All right, next up, how many pi in single bonds? All right, a sigma bond is defined as an end-to-end overlap. That's a sigma bond. A much simpler way is a sigma bond is just the first bond. There can only be one end-to-end contact, okay? So that overlap there, where they're essentially pointing at one another. So all of the first bonds are going to be sigma bonds. So if we look at this structure here, the first bond between every single one of these. So whoop, that counts as a sigma bond, that counts as a sigma bond, that counts. So every single first bond counts as a sigma. So there are 1, 2, 3, 4, 5 sigma bonds. So we can eliminate B and A. A pi bond is a side-to-side interaction. We see this with the pi overlap, these p orbitals. So this overlap here, that's a pi bond. It's side to side. This counts as one bond, although it's above and below, and it's all of the extra bonds count as pi bonds. So there are my 2 pi's, and there is my sigma bonds. So 2 pi bonds. So C. That's it. Simple, straightforward. First bond is sigma, the rest are pi. Which of the following have bond angles that deviate from the idealized bond angle? Yeah, so which of these have things that deviate? 1 second. Okay. So an idealized bond angle is essentially when there are no lone pairs. So all of the geometry with no lone pairs are pretty straightforward, or no multiple bonds. They're pretty straightforward. You're going to go based on what is actually there. But when you have lone pairs in the structure, on the central atom I'm talking about, that's when you're going to see deviations. So CO2, for example, and you can do all these Lewis structures, but I'm just going to do them quickly. And I don't really care about the peripheral atoms. CO2, this thing is linear, straightforward. We don't really expect to see anything crazy from that. Next up, BF3. So boron is one of these ones that actually is trigonal planar, and we end up with BF3, and that's it. There's nothing else on the boron. SF4. So sulfur is a little bit weird. Sulfur is going to have 4 fluorines. But we're actually going to have two electrons on that sulfur, and XeF4 So these are the two we have to choose between, because we can eliminate those because they don't have any lone pairs. So if we look at XeF4 and SF4, which of these is going to deviate? Well, the problem here is when you have lone pairs that counter each other, that are opposite of each other, they're going to cancel each other out. So C, we generally are looking for just a lone pair that's uneven. So SF4 is expected to deviate from the expected geometry. Much like if we looked at our previous example of this XeF4, XeF2, we would expect that one to deviate potentially as well. Although actually this one's probably linear, or the actual one is linear. So, but yeah, generally when you have just like one lone pair, you're going to see deviation. We see that in water, and we see that in NH3 because it's not 109.5, which is expected. We do see those shapes. Next one, which of the following molecules will have a trigonal planar electron pair geometry? So trigonal planar electron pair geometry. So we're not talking molecular geometry. We're talking electron pair. So NH3 is NH3 is going to be, again, I would encourage you to draw these out. This one is trigonal pyramid. Water is bent, but it's got 4 electron groups or 4 domains. And this is tetrahedral. This one also, water also has 4 electron groups, so that's tetrahedral. CH2 or H2CO. This one here is going to be a trigonal planar set of electron groups because it only has 3 electron groups. That is trigonal planar. And then finally CLF3. This one is going to be a bipyramid, a trigonal bipyramid, because it's got 5 electron groups. So your answer for 66 should be C. All right. What's the shape of PCl3? Oh, this is an easy one. P Cl, 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 and they all have 6 electrons each. There it is. 4 electron groups. So that makes it tetrahedral. This tetrahedral electron group geometry, but the molecular geometry is going to be trigonal pyramid. Trigonal pyramid, C. A lot of C's. There we go. All right, moving on. 68. What will the molecular geometry of a thing with 5 electron groups? So we're talking about a central atom with 1, 2, 3, 4, 5. It's going to be a trigonal. I'm going to put in little dashes because it's always easier to see is the inorganic chemist in me coming out. So that is the equator, and we have 1 axial, 2 axials, and we've got 3 equatorials. These are 90 degrees. These are 120 degrees. Around the central atom, 2 of those groups are lone pairs. So we have to decide which ones are lone pairs. It's always easiest to replace the top and the bottom with lone pairs. Top. Actually, sorry, no, actually we are going to replace the equatorial ones. So 1, 2. So let's replace this with a lone pair. Actually, it's going to be easier to do the other side to be able to see it. We're going to replace this with a lone pair, and then replace this with a lone pair. Okay. Yeah, so if we replace that with a lone pair, that gives us something that is T-shaped, D. And that one is, yeah, that one's D, 68, yeah. All right, moving on. Which of the following molecules is nonpolar? So you're going to draw these out and you're going to essentially look at them in terms of polarity. So I can tell you right now it's going to be CO2. CO2, here's my C double bond O's. And then if I actually look, the oxygens are pulling the electron density away. And because they're pulling out equally, they're equal and opposite, they're canceling each other out. Polar bonds will always form between the only nonpolar bonds, the list of nonpolar bonds. Any combination of carbon, hydrogen, sulfur, or phosphorus, those are nonpolar. Every other, you don't need to know electronegativities. Every other bond is going to be considered polar. Okay, so if it contains carbon, hydrogen, basically any combination of these two. So if I have carbon and hydrogen, or carbon and sulfur, or carbon and phosphorus, or phosphorus and sulfur, any combination of those is nonpolar. Everything else in the periodic table is. All right. What is the hybridization of the central atom? So we have to draw the Lewis structure. And I think we did above, XEF, F, 1, 2, 3, 4, 5, 6, 7, 8. There's my Lewis structure. Hybridization of the central atom. This is really easy, actually. This is what I want you to do. I'm going to write 1s. After s, we're going to get 3 p's. And then we're going to get 1, 2, 3, 4, 5 d's. And after that would be f's. But what I simply want you to do is write all of that out and then decide, okay, 1, 2, 3, 4, 5 electron groups. And I just want you to highlight the first 5 letters. 1, 2, 3, 4, 5. So 1s, 3 p's, 2 d's. Oh, I did one too many. Let's back up. One more time. I'm just I'll underline it because it's easier that way. 1s, 3 p's, that's 4, and then 1d. So my hybridization for this is sp3d. sp3d, C. Your answer 470 should be C. The number of electron groups essentially tells you, just underline. So if it's 2 electron groups, you have sp hybridization. Yeah, I mean, in this case, sp, this is 2 electron groups. Anything with 2 electron groups, sp. sp3, this is 4 electron groups. sp3d2, this is 6 electron groups. So just that's it, the easiest way to do it. All right, 71. Which orbitals overlap to form a sigma bond between sulfur and fluorine atoms in the SF4? Okay, the sulfur and fluorine atoms in SF4. So let's draw the Lewis structure. S. I'm going to draw the 4 fluorines. F. Let's see, back up here. So F, 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 F. We're going to put that lone pair on sulfur. Yeah, okay, SF4. So first question is, what's the hybridization? I have 5 electron groups. That means sp3d, hybridization of that. So we're going to say A from the sulfur. So we can eliminate this, we can eliminate this, and we can eliminate this. All right, there's our answer. And it's the 2p of the fluorine, because fluorine's in the second row. So there we go, A, easy enough. Look at the hybridization of the central atom and you're good. Which of the following schemes allows the formation of at least 1 pi? So in order to have a pi bond, you have to have a free p orbital. So if I do that thing again, sp, p, p, d, 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 what you really need is I can have pi bonding as long as I stop here. Okay, so sp, sp2, and that's it. Those two would have this extra p orbital available. So you need that p orbital in order to have that side-to-side p interactions. So sp or an sp2. So that would be allowed. That doesn't, that doesn't, that doesn't. So B is going to be the answer here. So you need to have this. That's the most important thing for hybridization, that extra p orbital that has not been hybridized. Next up, which substance has the lowest boiling point? Lowest boiling point is going to be the thing with the essentially the smallest thing, and also the thing with the least number of intermolecular forces. This has dispersion forces, and that's it. The answer is A. CF4, it also has just dispersion forces, but it's heavier than CH4. CH3, this one's polar. So this one is going to have dispersion forces, London dispersion forces, as well as dipole-dipole. And HCBr4 is larger than the others, although it just has dispersion, or LDF. I guess I'll just say that. That's what I mean by dispersion, LDF. LDF, London dispersion forces. But the smallest, the lighter it is, the weaker those LDFs are. And if that's the only thing holding it together, then that's the lightest. Which of the following is going to go through hydrogen bonding? Okay, in order to have a hydrogen bond, we need a super electronegative atom. So where X is equal to nitrogen, oxygen, or fluorine. So that's what we need. And then we need a lone pair on nitrogen or oxygen or fluorine. So first thing I need to do is I need hydrogen attached to nitrogen, oxygen, or fluorine. Nope. 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 Answer is D. That's it. Just eliminate the ones without nitrogen, oxygen, or fluorine, and that's it. You're looking for an OH, you're looking for an NH2 or 3. You're looking for that's pretty much it, pretty much. All right. Which of the following process is endothermic? And this is what I tell my students when I'm talking about endothermic. Why do we sweat? We sweat to cool ourselves down because evaporation is an endothermic process, right? We sweat and that allows us to cool down. So our body puts liquid water on the surface of our skin. and it turns from liquid water to gaseous water because it evaporates. That's what sweat does. This is endothermic. So anything going from solid to liquid to gas, that costs us energy. So solid to liquid to gas, solid to liquid, yep. Gas to solid, nope, that's in the other direction. Gas to liquid, nope, and that's in the other direction. Liquid to solid, nope, that's in the other direction. Our answer is B. When we're dealing with evaporation, when we're dealing with these things, that's what we're looking for. Which is expected to have the largest dispersion forces? Size matters, okay? So the bigger it is, the larger it's gonna be right away. All of these are gonna have, everything has dispersion forces. Just find the biggest molecule you can. That's one with the largest dispersion forces. 77, predict the formula of the binary ionic compound. Okay, I'm going to create, binary means just two things. So I'm going to combine magnesium along with phosphorus. Magnesium is expected to have a 2+ charge because it's in group 2. Phosphorus is in group 5, so I have a choice. Lose 5 or gain 3. It's going to gain 3 electrons. So I'm just going to take these numbers, give that to phosphorus, give that number to magnesium. So magnesium gets the 3, sorry. Phosphorus gets the 2, Mg3P2. Mg3P2. There we go. So C. What do we got left? All right. Last little bit. Select the answer where the compounds are listed in increasing melting point. Again, we're looking for things with the most intermolecular forces. So the highest intermolecular forces. So if it's ionic, it is going to be a high boiling point. If it has hydrogen bonding, that means it has all the other bonding as well. That is next what we're looking for. Then is it polar? Because that's going to give it dipole-dipole. And then last is anything with just London dispersion forces. So out of this list, I'm going to highlight anything that is, I'm just going to use the bottom one here, and then we're going to order it. K2, that's ionic. So is barium oxide, that's ionic as well. So those two right there. So I would probably pretty much eliminate, yeah, because order of increasing melting point. So those have higher melting points, K2 and BaO. So we're kind of selecting between those two. And then the choice between this has hydrogen bonding and this one is just LDF because it's all carbon hydrogen. All carbon hydrogen essentially leads to London dispersion forces, and that's pretty much it. So the question is barium oxide or the potassium 78. So yeah, when it comes down to ionic compounds, it comes down to lattice energy and more importantly, charge. These are both +2. One of those is +2, or that is +1. So actually it's going to be D. The greater the charge, the tighter the lattice is held together. All right, 2 more. Which of the following is not an oxidation reduction reaction? Single replacements, single replacement, single replacement, those we can eliminate right away because we have to have oxidation and reduction for those. So I'm going to eliminate those. Single replacements are absolutely oxidation reduction reactions. Also, we typically see anytime you have an element, it's also going to be oxidation reduction. An element has to, it's neutral when it's by itself, so we know it's got to have it. And if we have just an element, that means it gets oxidized. And if something gets oxidized, it has to get reduced. Something else has to get reduced. You can't have one without the other. So the answer for this is going to be C, just because I am looking for elements. If I have an element, it is C has no elements. That's all we're looking for. And then finally, which of these could represent the ground state of the p-valence electrons of oxygen. Oxygen has 6 electrons. Oxygen has 8 electrons, but so 1s, 2s, 2p, 1, 2, 3, 4, 5, 6, 7, 8. So that's what it should look like. That's the p. This is what we're going to focus on. So we expect B. That's got too many electrons. This is a violation of the Pauli exclusion principle. And this won't happen because we generally have, they want to go in the same direction because we want to have as much things going. We want to maximum multiplicity. We want these things to be facing in the same directions if we can. So B. And that's pretty much it. All right.